Welcome to this NPTEL course on Advanced Basis Concrete Design. We are in the module 10. Now, we will be looking at the part 2, particularly focusing on the PT two-way slabs. The expected learning outcomes after the student goes through this part should be able to understand the design process of PT two-way slab systems and gain knowledge on the analysis methods for post-tension system, particularly the design considerations, learn about stress checks and other considerations for edge and corner panels to see what are the additional reinforcement required in the design. In the subsequent part, we will be talking about in detail about equivalent frame method. Then we will take out one typical practical example and see how we can use equivalent frame method, and then compare the results with commercially available package such as SAFE. Okay, now just to recap, what is a two-way slab? Two-way slab, when the ratio of long to short is less than 2, it is called a two-way slab. For a slab panel, if you take the dimensions, divide the longer dimension to the shorter dimension, if it is working out to be less than 2, it is called a two-way slab. So, it indicates that it has significant bending in the two orthogonal direction, and the slab panel is going to bend in the form of a dish, right. So, accordingly the main reinforcement is required in two directions, right. This is the panel that you talk about. Let us say this panel is supported on all the four sides. When you apply a load, you can see that you are going to have a bending like this, right, and then also in this side you are going to have bending like this. So, you will have significant bending in two directions, but if you get close to the support, as you can see, right, you can the deflection profile and the curvatures are going to be small. So, it depends upon also where you are looking at the section. This is a typical, you can see the slab that is supported on columns, and you can see for strip 1 and 2, the moment profile will be like this. For moment strip 1, which is close to the mid location, you are going to have higher curvatures and higher moment, but however for strip 2, it is going to be lower, right. So, this is for the strip number 4 in the orthogonal direction, which is spanning along L1. So, you can see that there is also going to be a significant moment, because this section is also 4 is along the mid section, mid length. Now also the behavior between two-way and one-way, it also depends upon how the slab is supported. Let us say for example, if a slab is actually supported on two edges like this, right, then the bending is going to be only between the supports, irrespective of the geometry of the panel, right. So, these two are, so that means the other two sides are actually unsupported, they are all free edges. So, that means the load has to be transferred to the support. So, the slab has to bend only in one way action. So, it is the two way or one way action is not only about the span to span ratios, it is also about how it is supported, right. For example, you see here this is a two way slab which is supported on all the four edges, which are simply supported. Then you can see that the deflection contour is going to follow like this. It is going to have high deflection here and low deflection here and so on, right. Close to the support, your deflections will be 0 because they are supported. Now, the load transfer also, you can see here whatever the loads that are applied, that will be getting transferred to this edge in this form, like what we have seen, like that this load will go to this support. Similarly, so we can divide the panel into trapezoids and triangles and then see how much load is getting to different supports. Now, again the variations of the short span and long span moments that you can see here are the profile that is here, which is mx and my moments that are coming here. So, you can see that for a two-way slab, as we have seen, you will have higher moments in both the directions, because it is bending predominantly or bending significantly in both the directions. However, if you take a slab with a long aspect ratio, you will have bending moment, higher bending moment only along the shorter direction, in the longer direction, I am going to have smaller bending moment, because the curvature is not going to be there. So, again bending moment, you know that it is in a simple way, it is basically m by I is nothing but your curvature d square y by dx square. So, higher the curvature, higher will be the bending moment. So, you know from simple bending theory. Now, we are talking about post tension slabs which are going to bend in the two directions, right. So, in the previous part of the module, we talked about one way slab, which is very similar to a beam design, one way beam design. So, now we are getting into the two way PT slabs. Now, the first thing whenever we design is to find out the thickness of the slab and also find out what is the amount of pre-stressing that is required and the layout of the tendons, right. So, for factors determining the slab thickness, as you know, deflection is the main criteria for slabs, because again two way slabs are highly redundant. The strength is typically not a concern, it is the deflection that will govern the thickness of the slab. So, typically we get it from L by D ratios. The PTA manual gives you values that we have discussed. Typically for two way slabs, you can go up to 45 to 50 depending upon whether you have flat plate or flat slab or slabs with beams. So, the ratios are given, we can use it. Then we should also, sometimes if you are doing a flat plate, again the shear stress will determine the thickness of the slab, that is what we are saying punching shear. Then the span arrangements, how you span arrangements are there, that will also influence what kind of bending moment that it is coming and what kind of reflection that the panels will have. So, these are the typical factors that will actually govern the slab thickness. Now, amount of pre-stressing actually depends upon the pre-compressive stress required. Typically, pre-compressive stress we target for roughly about 1 megapascal average stress, right, and how much balancing load that we are trying to get from the pre-stressing, again we try to balance about 100% of dead load typically, and then we also need to try to adjust the profile according to the span arrangements. So, what is the meaning of span arrangements? Depending upon the ratios of the length of the span of adjacent spans, then we have to slightly adjust the profile, so that you are not going to have a very high significant bending moments only at few locations. Please note that in post tensioning, you are running the cable along the entire length of the member. So, we need to choose the configurations in such a way that you are going to get more or less similar amounts of bending moment for design, so that you can come up with an economical design. Now, also it depends upon what is the uplift required. The pre-stressing will depend upon how much uplift required. For example, if you want to, for a long span, if you want to limit your long term deflections, typically we go for slightly higher camber. So, how much that you want to contract the self height. Again, the amount of pre-compression, for example, if it is a roof slab, then due to the rain, the water tightness may be governing the design. So, you may end up with slightly putting higher stress. So, the amount of pre-compression, which is P by A, it will depend upon how much you want to mitigate the cracking and how much you want to reduce the deflection, and also how much, if at all you want some strength. Of course, always we can use the TMT rebars, normal non-pre-stress TMT rebars for additional strength, but the amount of pre-compression also depends upon what are these parameters are required from design point of view. Okay. When we do the analysis, we have now typically three options are done. The first is a very widely used, which is called simple load balancing, that we have discussed it previously in the introductory modules. How do you create the loads using load balancing concept? Then we also have another method which is proposed by Mr. Alami, which is extended load balancing method. Then the second approach is tendons will be left in and they will be considered as a reinforcement with the initial stress, that is another approach. The third thing is you do not consider the design in the tendons at all. This is not really typically procedure. The tendons are actually not considered for both service and strength. You basically design it like a RC slab, which is not really correct Okay. So, but this will lead to very unconservative design, right. So, typically it is not done. Typically sometimes the design officers, if they do not have the Excel sheets, if they want to have a quick conservative design, then they can do like that, because also if sometimes if the PT is provided is very less, just to ensure some uplift, then for conservative design sometimes they ignore it, but more common method is this load balancing concept. Right. So, what is that load balancing concept? Simple load balancing concept is based on the constant force, and we are going to decouple the effect of axial and bending effect. In extended, that's we know how to get the balancing loads and moments that is created by pre-stress. We have already studied in the previous module, so you can look at the previous videos for more information. Right. We know that for a parabolic cable profile, it is going to create a constant vertical load along the length of the span, right. When you have a linearly varying cable profile, you know that it is going to create an upward force wherever the cable is changing its cable profile. So, how to create the balanced loads for the pre-stressing profile, we have already discussed, so you can look at the previous module. Now, in extended load balancing, it is allows for the change in the centroidal axis of the member, right. For example, when you have a PT slab, flat slab, you know that your slab regions where you have a drop panel, your CG of the section will change, right. So, you can use extended load balancing to capture the change in the centroidal axis of the member. So, basically it is an extension of the load balancing concept it was proposed by T.Y. Lin. So, for example, this is a very typical case. You have two span system where you have one span with a particular thickness, the second span is having a larger thickness, right. So, then you have a cable profile like this. So, this is the member with some change in your centroidal axis, right. So, this is the example that again we are discussing. Now, how do we include this effect? So, we are decoupling this into two effects. One is the axial effect and the bending effect. Let us see now how do we consider the axial effect. So, for example, we know that though the cable is under tension, we are looking at what is the effect that is produced on the concrete, and you see that this element, if I put the force at only axial effect, if I look at it at the CG, it is going to be P. Now, the next element, the P will get shifted, right, and this is the way that I consider the axial effect. But of course, because of the change in geometry, you are also creating this moment that also has to be considered. So, that is being considered by applying a moment like this, which is equal to P into A. So, this action will cause the flexure of the member, and this type of scenario is observed in slabs with drop panels over the column, right. So, in this way, when the CG of the members are changing, we can use the extended load balancing concept to model the change in the geometry by decoupling the pre-stressing effect into axial and flexure. Now, very important for a PT slabs which are continuous in nature, you are going to have hyperstatic effects which are also called as secondary actions. We have again discussed this in the module on continuous beams. So, for example, if you have a simply supported member and these are unstressed on the supports and this is an unstressed isolated element, when I am applying pre-stressing, you know that it is going to bend in the form. For example, let us say apply a pre-stress like this, right. So, it is going to deform and the support also will allow the deformation. So, it is going to move down. So, you are not going to develop any additional reactions, right. So, and the member can undergo deflection like this due to while you apply the pre-stress, right. So, and stressed elements will be actually be compatible, right. So, typically when we do it, let us say usually when we apply constant eccentricity, you will get this bending effect, right. So, let us say your CG is here, right, and you have some eccentricity. Let us say that I have right, and this is your eccentricity E. Right. However, for statically determinate systems, we have seen that due to the applications of pre-stress, I am not going to develop any additional reactions. So, the secondary moments produced will be 0. Now, let us take another typical case. You have a beam where I am trying to apply some pre-stress, right, and there is a column that is connected at the intermediate support. Now, for this element, when I am trying to do the pre-stress, obviously this is a statically indeterminate structure. So, when the member is trying to squeeze the supporting elements that are connected, it will not allow it to freely move. So, it is going to create this kind of reactions, right. So, all these reactions are created, and these reactions again will produce some additional moments which are called as secondary moments. So, for example, while you apply the pre-stress, the member tries to deform like this. Of course, this is done in a very exaggerated manner. So, it is going to deform like this. So, you are going to develop some reactions like this. That reaction will have moment will be produced like this, right. So, these are the moments that are here. This is moment 1, let us say this is moment 2, and these are your reactions, right. So, all these things will create this secondary forces and moments for this particular beam element. Okay. We are looking at only the beam element, right, because here we are trying to apply, for example, only the pre-stressing on the beam. So, the beam will be subjected to some secondary forces and moment, and the secondary moments have to be considered when you go for a ultimate strength design. So, when we do the strength checks, the effects of hyperstatic moments have to be considered. Okay. Now, what are the design steps? This is what we said. Of course, the amount of pre-stressing is governed by the stress limits. So, the load combination that what we are going to use is 1 times dead load plus 1 times live load plus 1 times PT. Now, what is PT? PT effect is the direct load effect of pre-stressing, which is applied along the tendon profile, independent of the boundary restraints. That means, the pre-stressing will induce concentric pre-stressing force, and then if you have an eccentricity, that will also introduce moment. So, pre-stressing moment and the concentric axial effect of the pre-stress has to be considered, that is called PT effect. However, for safety conditions, for strength checks, this is for strength. When you are calculating whether the provided PT cable is really adequate for that moment, then I need to use, for example, if this is as per ACI, right. So, if you are using IS code, I will put 1.5 DL plus 1.5 live load plus 1 times hyperstatic moment, right. So, this is as per ACI code, right. So, we have to consider the effect of your hyperstatic effects, right. What is hyperstatic effect? It is again the additional effect due to structural indeterminacy and compatibility conditions. The additional moments that are developed because of the pre-stressing, because the structure is structurally indeterminate, has to be included in your strength calculation. This is as per IS code, ultimate strength. Okay, this is as per IS code. Right. And this is your service condition, right. So, these two conditions. Of course, if the amount of cable is not adequate, then I can also use TMT rebars or a non-pre-stressed steel as an additional reinforcement from strength, right. That always we have that option for the design engineer, right. Now, for let us look at, we looked at the two different important states. For service conditions, we are going to use the post tensioning balanced values to calculate the deflections, check for stresses and cracking. Now, for ultimate conditions, we have to use hyperstatic secondary moments, because again we have seen that the secondary moments, including the secondary moments, will be beneficial. It is going to reduce the negative moments in design. We have studied that in the continuous beam. It will also, but at the same time, it will also increase your positive moment. But overall, if you look at it, if you include your hyperstatic moments, in a way, it is going to be, it is going to reduce your design moments at the support locations in general for a generic loading. right. Now, what are the design steps? As we have explained, first we have to check the service state, which is called serviceability limit state. In fact, we design the amount of pre-stressing to satisfy the stress limits. Then we check for safety, whatever the PT amount and profile that we have chosen to satisfy the service stress condition. We also need to check for safety, whether that provided reinforcement is able to take care of the bending moment that are developed along the length of the member, right. If it is not, only PT is not sufficient, then I can put PT cable plus some TMT rebar. The TMT rebars, as you know, they are also called as non-pre-stressed rebars, right. Now, then these are the steps. Then we should also check, as you know, there are 3 stages that are there usually. One is the transfer stage, the next one is the service stage, next one is an ultimate stage. These are the 3 stages that are we need to check for. So, the initial stage is the transfer of pre-stressing, and then the serviceability limits specific to PT reflection. For we should also check for cracking and vibration. Then we need to check for safety, which is adequate resistance to bending and shear. Now, the initial condition and stressing also, while you do the transfer or we apply the pre-stress, we have to be careful so that we are not going to create localized crushing or also cracking at the locations away from the pre-stressing cable, and the creep effects also have to be considered, right. These are the typical design steps that we check for. Usually, the dimensions and the amount of pre-stressing and the cable profile comes from your service conditions to satisfy your stress limits. Then you go ahead and check for your ultimate strength. Then, but in the process, after finalizing everything, we should also make sure that all the stages you are satisfying the stress limits.